The next enthalpy that we shall experimentally determine is the enthalpy of precipitation. We have come across precipitation reactions way back when we were discussing how to prepare salt, and specifically insoluble salt. We said the precipitation reaction is a reaction between a soluble substance, a solution, plus another soluble substance, that is two solutions, to form an insoluble substance and a soluble one. That is what we call the precipitation reaction, and we also refer to it as a double decomposition reaction. So you know that when you prepare a precipitate, you must start with two soluble substances. I have seen some confusion where you add some, say, sodium, calcium carbonate to some water, then it doesn't dissolve. Then you say that is a precipitate. That is not really a precipitate. You could call it a solid, a residue, if you are going to filter it. But it is not a precipitate until it is obtained from a reaction between two soluble substances. So that is how you get to a precipitate. So the next question is, what is enthalpy of precipitation? Now, the enthalpy of precipitation shall be defined therefore as energy change. And now I suggest you use the energy change. Why? Because precipitation can either be exothermic or endothermic. So it is the energy change that occurs when 1 mole of a precipitate is formed from the constituent ions in solution. Now I have a vocabulary there, constituent. Of course, that just means the ions that makes it up. You could still do without it from the ions that makes it up. So you could just say from ions in solution. So the enthalpy of precipitation of silver chloride therefore may be the enthalpy of a reaction silver plus chloride ions to form a silver chloride in solid state. Of course, this must be from a compound like sodium chloride. This must be from a compound like silver nitrate. But all I'm interested in is the silver ions and the chloride ions. So when I end up with 1 mole of silver chloride, then I'll call that the enthalpy of precipitation. So if I am interested in the standard enthalpy, then I'll talk of the energy change when 1 mole of a compound is formed from the constituent ions in solution in standard state. So all I need to add to that is the standard state, and then it becomes standard enthalpy of precipitation. Let's attempt some examples, because what we are actually interested in this part of the topic is to calculate the enthalpies from empirical data. So that is a definition, by the way. A precipitation reaction, so it's also called a double decomposition. I've heard some people talk of double displacement. Now, of course, we are displacing, if we are talking of silver nitrate plus, say, sodium chloride, you are displacing the silver, you are also displacing the salt. So it's a double displacement. Unlike if it was silver nitrate plus say copper, you are displacing, that's simply a displacement. But this one you are double displacing. So that's yet another name, but it is not very common, double displacement. Let's stick to double decomposition. So the enthalpy of precipitation is defined as a heat change when 1 mole of a precipitate is formed from the constituent ions in solution. Then you can add at a standard state if it is a standard enthalpy that you are defining. The example, there we are, and you could pause and wrestle with it. You could pause a video, wrestle with it, and see whether we get to the same thing. So you are given all that data. Please read through and try. So let me read it with us. 25 cubic centimeters of 0.1 mole barium chloride solution is mixed with 15 cubic centimeters of 0.25 mole silver nitrate solution. Of course, the two are going to react to form the insoluble silver chloride. Both of them are at 24.5 degrees Celsius. What is the final temperature of the mixture? Given that the equation of a reaction is that, and you don't have to be given the equation, you should be in a position to write balanced chemical equations. So that's, and you're also given the enthalpy of that particular reaction. So let me note something about that. So this is a thermochemical equation, as what we have already said. What does it tell you? When 1 mole of barium chloride reacts to 2 moles of silver nitrate, it forms 2 moles of silver chloride and 1 mole of barium nitrate, then that amount of energy is produced. In fact, you could say therefore that the enthalpy of precipitation of silver chloride is 100.16 kilojoules per mole, because this energy is for 2 moles of, that is for 2 moles of silver chloride. And I think in my opinion, I think, and I start to be corrected, that whatever you use to produce a silver chloride, the enthalpy of precipitation of silver chloride is always going to be 50.16. It doesn't matter what I use. Even if I use sodium chloride, because all these are spectators. All those are spectators. If I use sodium chloride, the sodium is going to be a spectator. Of course, I cannot use anything apart from, I can use the sulfate maybe. The nitrate is soluble. The insoluble salt of silver could be the chloride, and of course carbonate and the sulfide. So whatever I use as the whatever is accompanying the silver is simply going to be a spectator. So for silver chloride is always going to be 50. And I think that is what I would say from that reaction. So you need to be in a position to interpret a thermochemical equation. Now I hope you've made a lot of noise, so you could pause and attempt that question. Welcome back. Yeah, I hope you went. Yes, so you've not been waiting for me to do it so that you can copy. Yeah, let's. So how did I go about it? Now the energy change for this reaction is the mass, the MC delta T, where M is the mass of the mixture this time. So what is surrounding the thermometer? It is the barium chloride, the 25 and the 15. That is what is surrounding the thermometer, and that becomes my M value. Remember, in the displacement, we said you ignore any solid, but you don't have solids here, so we are not ignoring anything. We have to add up the 25 to 15. That becomes our M value. Then the specific capacity is given. Now the delta T, where is it? I don't have the delta T. I only have the initial temperature. I need to work out the delta T. So I should get some more information. What is the other information that I need? So I cannot have two unknowns, heat change and the delta T. So, but from the equation, I can get the heat change, the energy change. Now, do I use 100.32? Of course, that doesn't make sense. Why? Because this would only be the case if I had 1 mole of that and 2 moles of silver nitrate. I don't have that. You can see I have 25 of 0.1 mole. I have 15 of 0.2. So I don't have a mole of either of them. I don't have a mole of barium chloride. I don't have 2 moles of silver nitrate. I have to get exactly how much I have. Right? That is what I've done from that. That is from the simple molar solution of form 3. I hope you are very conversant with that. So work out that and work out that. Now, I don't have, the ratio is not 1 to 2 even. It's not 1 to 2. So I need to find out which one is in excess. We have done that many times. Now, if I used 1 mole of barium chloride, I would need 2 moles of silver nitrate. Now, let me assume that this is the one that reacts completely. So, if I have 0.025, how many moles of silver nitrate would I need? Of course, I need 2 times that. That is 0.0005. But I have 0.00375. What do you think that means? Of course, I have less than I need. What does that mean? That the barium chloride cannot react completely. If it were to react completely, I must get somewhere and borrow some 0.125 moles. I'm not going to borrow. I am not allowed to borrow in this particular case. So it means that not all the barium chloride can react, but all the silver nitrate will actually react. All the silver nitrate will actually react because I have more than enough. Because if I divide this by 2, I'll have 0.01 something. But I have more than enough of that. So all the silver nitrate react. So it is a silver nitrate that I'll use in this equation and not the barium chloride that is already in excess. So, but 2 moles of silver nitrate would, so from the equation, 2 moles of silver nitrate would give me 100 kilojoules of that. But I have only 0.0375, so that is the amount of energy that I'll have. Now, so I have another known here. I can put the known right here. That is a 0. And of course, this is going to be in joules. Yeah, that is important. Whatever energy I get here is going to be in joules, but this is kilojoules. So I multiply by 1,000. So I can just get the value of delta T. So this question, there are only 2 tricks therefore in this question. The first one is knowing that you cannot have 2 unknowns. You cannot get a whole 1,000. One of them will have to be excess. You find that excess. If you do that, you are halfway through. Then get the amount of energy, but remember that is in kilojoules. So it has to be converted to joules. So by multiplying by 1,000, I can get the delta T. It is 1.112 Kelvin. Changing temperature in Kelvin the same as changing temperature in degrees Celsius. So I just need to add that to 24.5 and get the final temperature of the mixture. I hope you got that. Yeah, I hope you got that. If you did, you can cheer yourself. Cheer. You are a bright one. You are headed to an A. So the next thing that we need to do is to experimentally determine the enthalpy of precipitation. And I've chosen to experimentally determine the enthalpy of precipitation of copper 2 hydroxide, of course. Now, but so I have 0 for the person preparing the reagents. You can prepare 0.9 molar copper 2 hydroxide and around 2 molar sodium hydroxide. You will do it will do, the experiment will work as long as we don't have equal half of these. Because if it is half, they are going to meet at a plot, and if curves meet at a plot, then they are not extrapolated. That is all that you need to consider. Then the experiment can easily be done. How are you going to go about it? I will just measure 5 cubic centimeter portions of sodium hydroxide and press them. I think I'll have around 8 test tubes. 8 test tubes with 5 cubic centimeters of sodium hydroxide. Then I'll press 20 cubic centimeters of the 0.9 molar copper 2 sulfate in a plastic beaker. I'll use a glass beaker because I want you to see, but it is not advisable to use a glass beaker. especially because you'll be stirring with the thermometer. The thermometer will break, and also there is also a lot of heat changes. There are a lot of heat losses to the surrounding. So a glass beaker, plastic beaker is recommended. Then I will take the temperature, the initial temperature of the copper 2 hydroxide in the plastic beaker, and then immediately add the first 5 cubic centimeters of the sodium hydroxide. I'll know the maximum temperature reached, and so after I've stirred a bit, but make sure that you don't stir forever, because the more you stir, these are in these reactions, the temperature rise. When it gets the maximum, it's supposed to start cooling towards room temperature. So you should immediately, the word is immediately. Immediately you are through with correcting the data for the first one, get to the second one, do that as fast as possible. Some students have a tendency of stirring forever. You may get everything constant, and some even have the tendency of putting it and then observing, removing it from the solution and observing. Is the temperature changing? Of course, it is going to remain constant forever, and you complain that the thermometer is not working. So, but what am I doing? What are we doing? We just adding 5 cubic centimeter, stirring, noting the final temperature. Then to the same, you add another 5 cubic centimeters. There will be a rise, and you continue rising and rising until you add the last. Now, the question is, what am I expecting? Then you will complete the table, and the table will look like that. So actually, from this point, I will allow you to fill that table. I've done the experiment for us or for you. All you need to do is to correct the data. Read the highest temperature that is attained. Now, so you read and complete that table. In this experiment, the enthalpy of precipitation of copper hydroxide will be determined. So I have 20 cubic centimeters of copper 2 sulfate, to which I'll be adding sodium hydroxide in 5 cubic centimeters portion. So what the student will be expected to do is to take the reading after every portion has been added. Assuming that you have read the data, what were you expecting? What are you expecting? Because as we said, the theory must agree with your experiment. Now, we are expecting the temperature to rise or drop. If it is endothermic, it should drop. If it is exothermic, it's going to rise. So rise up to some certain point where it should not rise again. Yet you are continuing to, when the reaction is over, you are continuing to add some cold sodium hydroxide to that. Yet the reaction is over. So whatever sodium hydroxide you'll be adding after the reaction is over will only cool the mixture. So the temperature should rise and then drop. So if you don't get that, there is something wrong with your experiment. You need to redo the experiment if you can, or somehow ensure that is what happens. It should rise and then should drop. I expect you also to take some time and plot a graph of temperature in the vertical axis against the volume of sodium hydroxide. Please do that, and let's meet after you have done that. Hope you've paused the video and proceeded to draw the graph. Here you are, that is what I got. That is what I read. Now compare your values with mine, see if mine could be wrong. I'm sure there is somewhere where we are going to differ around that point. Why did I? There's some value here. I'm sure there is some value there that is going to be different. Why do I have a different value? Because we said that now this table, the last time I saw it in an exam, was carrying about 4.5 marks. Now, so there'll be 1.5 marks for completing the table. There'll be a mark for the decimal. There'll be a mark for accuracy, and there'll be a mark for the trend. Now, the 1.5, we said you always need to get it as long as you do the experiment. As long as you do the experiment. So, and I told us a long time ago that there is a way of knowing that you did not do the experiment. So don't think you are going to call the examiner. So the decimal mark, whole number or one decimal, consistent, never two decimals, consistency, the accuracy, this is a value, not that we are very afraid here. We are going for the value that is easiest to get. So plus or minus 2. Now the trend, that is where I change. That's why I changed one of the values, because for me it was, from what I read, it was coming to 25.5, then 25, another 25. So it should be a constant rise, then a continuous, not constant, a continuous drop and a continuous. But when I get 25 and 25 again, 25, 25.5, 25, and another 25, it has dropped and then has remained constant. So I had to do something about that. I don't know whether that is around in your world, but that's what I did. That's what I did. And that is what I expect, because I don't expect us to just lose marks. So that is how that table will be marked. Then the next is the graph. Can you mark your graph? Mark my graph too. How did you mark it? The scalp. The scale. Do the plots occupy at least half of that paper? Count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, 11 out of 15 is of course more than a half. So I have, and is it consistent? Is it accommodating? I have half a mark. Now check yours. And be very keen about the zero. I keep repeating zero because it's a very costly mistake. if I put a big 0 here, now check what you did after you put a 0 there. Of course, you may have decided to extend from 0, 1, 2, 3 or 2, 4, 6, 7. You lose a scale mark. You lose a scale mark because your graph is going to be very small. It's going to be very small. Note we are counting the space that is occupied by the plots. The space occupied by the plot, the first plot and the last plot. You have, I'll see people with the paper that is that size, and then they write 0, 1, 2, 3, 4, 5, 6, 7, up to 20 around there. Then they will draw a graph right there. They'll draw a graph right there. Then they will tell me, but these plots are occupying, this graph is big. You see, I've written the scale. We are not interested in where you've written. We are interested in your first plot and your last plot, not the scale, how big you have distributed that. That's not what you're interested in. It's the first plot and the last plot. Now, so this 0, what did you do when you wrote a big 0 there? Did you write your 20 there and then you forgot to break your axis? If you do that, you've lost the scale mark, you've lost the plotting marks also, you've lost everything. You've only gotten a mark for the axis. That 0, that's how that 0 is expensive. That's how that 0 becomes. So make sure that you are familiar and conversant with that. Be very careful about that. So back to the graph, of course, I have that mark, I have the axis. Of course, I labeled the axis, drew the line, drew the arrow, then the axes are labeled with the correct unit, temperature in degrees Celsius, not in degrees. Volume in cubic centimeters, not in centimeters. Then the other, after axis, then you have the plotting. Ensure that your plots are feasible and they are as accurate as possible. Don't round off. Don't round off. Then of course the curve, is it extrapolate? I chose the 3.123 points. I joined them. You could choose any other, but I think with the 3 points, they are more. I have only 1 point that is not on the line, and they are actually 2. Then the other one, I used as many points as possible. Remember, extrapolation, meeting above the highest and not meeting at a plot. That's all you need to consider. So it cannot be, even if I decide to use these two, it will still be correct. I've decided to use those two. Even if I decide to use this, I leave all these and I use just that too. As long as I'm meeting above the highest, so it's at your discretion. It's at your discretion to decide on the plot that you are going to use, as long as they are two correctly plotted plots. But the more you join, the better. So that becomes my graph. So let's proceed to use a graph. What is the first thing that I need to do? One, determine the volume of sodium hydroxide that reacts completely with 20 cubic centimeters of the copper sulfate. Now the showing, remember to show it. Now look at my graph. I did show. So I showed and read. Now to me it is coming to around 18.75. It's between some two small boxes. I can show and decide to read that as 18.5. So I know that it's between that. Maybe I'll get the mark for showing. I'll lose the mark for reading. Because it's not really 18.5, it is 18.75. The same will apply to that. So be in the habit of showing, because you can still get half a mark for showing if you did not read properly. Because the examiner will get back to your graph and read and compare with what you have given. If you don't read properly, then you lose those marks. Now, what is the next thing that I need to do? Get the heat. Calculate, find the enthalpy change per mole of the copper ions. So we know the way by now. So the total volume on compression. 20 is reacting with 18.75. Remember the significance of where the curves meet, where the curves meet, that is the point where the reaction is complete. So I'm using the volumes at that particular point. So I need to add up the two, then use a specific capacity. That's all I'm getting. K and K cancels, G and G cancels. The unit there will be joules. So the moles of copper used, I was told it is 0.8 mole. So 20 cubic centimeters of 0.8 mole, that is those number of moles. So 1 mole of copper, that much. The sign and the unit. Of course, I've divided by 1,000. I've divided by 1,000 to get the kilojoules. The small j, K, capital J. Capital J. So that is how we go about that. Now, having done that, I think you are ready for your own example. Wrestle with it. Wrestle with that example. You can pause the video. Actually, that's the end of my presentation for this particular concept. So you can take time and compare your answer with your fellow students. So what does the question read? In an experiment to find the heat of precipitation of magnesium carbonate, 25 cubic centimeters of 2 molar magnesium nitrate is added to 25 cubic centimeters of 2 molar sodium carbonate. So the temperature of the mixture decreased by 6 degrees Celsius. Find the molar enthalpy of precipitation of magnesium carbonate. I hope that can be done. I hope that is now, by now it should be becoming very easy. So we will proceed to the enthalpy of solution.